In this video, we're going to be continuing our discussion of calculating the pH of acid and base solutions, but this time focusing on weak acids and bases since we need to treat them very differently. So what we know about what it means for something to be weak is that only a small fraction of our molecules, our acid or base molecules, actually ionize in solution. So if most of our stuff, most of our acid or base, is remaining unchanged and only a little bit of our ions are being produced, this is something that is establishing equilibrium. So our reaction with water establishes equilibrium, which means that we can't use stoichiometry like we did for strong acids and bases, because we can only do that when our limiting reactant is being completely consumed. In this case, we don't know exactly how much of our acid or base is reacting, but we know it's not all of it. So we're going to need to use an ice table. In order to determine our hydronium concentration in solution, which is the equilibrium hydronium concentration, or hydroxide concentration if we're dealing with a base. And from either one of those two things, we know that we have a couple different ways that we can go about finding the pH. So, for example, we can calculate the pH of a 0.5 molar acetic acid solution at 25 degrees. I won't forget that this time. We would also need to know that the Ka of that acid is 1.8 times 10 to the negative fifth. So from here, this is a pretty typical equilibrium problem. You just need to recognize really that this is what you're looking to solve for, is either the equilibrium hydronium or hydroxide concentration, depending upon whether you're dealing with an acid or a base. So we're going to need the reaction that goes with Ka. So Ka always represents the reaction of an acid plus water in equilibrium with whatever the conjugate base of that acid is, and hydronium. So that's the general idea of what our reaction is going to look like. If we do that for acetic acid, we'll have our acetic acid HC2H3O2 reacting with water to produce the acetate ion is our conjugate base. When we have lost H plus from acetic acid, we're dropping this H that's out in front, and that takes a plus charge along with it. So if we're starting at neutral and losing a positive charge, we end up with a negative charged anion over here. And when water gains that H plus, it becomes hydronium. So we want to solve for, in this case, our hydronium concentration at equilibrium. So if we set up an ice table here, the concentration that you are given in the problem, wanted the highlighter, there we go. The concentration that you are given in the problem is, hey, went away. I hit undo, I didn't mean to. The concentration that you're given in the problem is the initial concentration. So that is the amount of acetic acid molecules that were put into the water initially before any of them had a chance to react. We put 0.5 moles in every liter. So our initial concentration of the acetic acid is 0.5 molar. Water is a liquid, so we can ignore that whole column. Before any reaction has happened, all we have is the acetic acid that we put in water. We do not have any acetate ion produced yet, and we consider the amount of hydronium already present in the water to be negligible. Technically, if you're putting this into pure water, it would be 10 to the minus 7th molar, but that shouldn't affect our calculations. So from here, if we have no products, we're going to need to create some product. So our product concentrations are going to increase, which means our reactant concentration is going to decrease. All of our stoichiometry is 1 to 1. All of our coefficients are 1, so we'll just have minus x on the left side and 2 plus x's on the right side. So we will have 0.5 minus x molar acetic acid remaining at equilibrium. We will have generated x molar acetate and x molar hydronium. So this is what we're looking to solve for here in order to be able to find our pH. We know that pH is the negative log of the hydronium ion concentration, so we need that equilibrium concentration of hydronium to get our pH. So we can do this just like we've always done, plug into our equilibrium expression. So our Ka expression always has the conjugate base, which is our acetate ion, times hydronium on the top, and then our acid on the bottom. And at this point, we can plug in everything that we know. So we're given the value of Ka up in the problem, and then we want to take these expressions and plug them in where they go. So I guess we had this one I did in blue and this one I did in blue, and hydronium was the one we were interested in, so that one kind of got its own color. So for the Ka, we have 1.8 times 10 to the minus 5th. The concentration of acetate is x. The concentration of hydronium is x. And the concentration of acetic acid is 0.5 minus x. So from here, we could recognize, we could do the quadratic equation and go through all the math and get our answer that way. Or we can recognize that we can simplify this. So this is one of those cases where K is small, meaning that very little product is produced. If very little product is produced, x is a very small number. So 0.5 minus x is effectively still going to be 0.5. So we can ignore this minus x on the bottom. K is small, so x is small. X is small. Grammar is good. So we can ignore added and subtracted x's. So we can say that this is approximately equal to x squared over 0.5, and that just got a whole lot easier to solve. So we find a value for x, which is our hydronium concentration in this setup, of 3 times 10 to the minus 3rd molar, and from there we know how to find the pH. The pH is just the negative log of the hydronium concentration, so that is the negative log of 3 times 10 to the minus 3rd, which is about 2.523. So one thing to kind of watch out for that can help you check your work a little bit, if you're calculating the pH of an acid solution, your final answer should be acidic. So a pH of 2.5 makes sense. If you came out with a pH of 9 here, that should set off some bells and whistles in your head, that this was an acid in water at room temperature. Your pH should be less than 7. So that's a nice little simple trick to know that something went wrong that should be easy enough for you to spot. to be able to go back and check your work if that were the case. So we can apply the same process to a weak base. Similarly to when we talked about strong acids and bases, the only difference is that we first calculate the hydroxide ion concentration, and then there's kind of just one extra step to get us to pH. So let's calculate the pH of a 0.5 molar sodium acetate solution at 25 degrees. Kb for our base is 5.56 times 10 to the negative 10th. So this is going to be very similar to the last problem. What we need to recognize here is that in this compound, the sodium is just a spectator ion. That the actual base is the anion, is just the acetate ion in sodium acetate. So from here on out, we can just ignore the sodium. We can drop it from our, we should drop it from our reaction. And that will make everything simpler. And the Kb is specifically referring just to the acetate ion. You will notice that the acetate ion is the conjugate base of acetic acid. So acetic acid is what we were dealing with in the previous problem, was this guy. The conjugate base that is produced is the acetate ion, sorry. And we said that the conjugate base of a weak acid is a weak base. So if you recognize that this acetate ion, if I slap an H+ onto this guy, becomes a weak acid, you know that that is a weak base. So you're now better able to identify what is or is not a weak base without necessarily being told. Although being given a Kb for something means it is a weak base. So that is like a giant red flag that this thing is a weak base. If it's a Kb, it's a weak base. If it's a Ka, it's a weak acid, even if it may not necessarily look like it is. So here we will once again want to write the reaction for Kb. It is always the base plus water in equilibrium with the conjugate acid and hydroxide. So why don't you pause here and see if you can give this problem a try on your own. So again, the base you want to use is just the acetate ion itself is what you want to put into this reaction. You'll want to write your reaction first. Set up an ice table, go through the usual equilibrium process to find your hydroxide concentration. Then you can find your POH to your pH, or then you can find the hydronium concentration to get the pH. Either one will get you there in the end. So pause here, take a moment, and try that one on your own. So the first thing we want to do is write our reaction. Our base is the acetate ion, which is going to react with water to produce the conjugate acid of acetate, which is acetic acid, along with hydroxide ions. And we can set up our ice table for this reaction. Once again, our initial concentration that we're given, the concentration that we're given in the problem is the initial concentration. It is how much acetate was put in to the solution before any of it reacted. So before any of that reacted, there was no acetic acid in the solution, and the amount of hydroxide would be considered negligible. So we can treat that as being 0. So this means that we're going to consume reactants and produce products to get to equilibrium. So we will have 0.5 minus X acetate remaining, X acetic acid produced, and X hydroxide produced. So to calculate our pH, the hydroxide concentration is what we need to get out of this ice table, is what we need to get from this equilibrium calculation. So as usual, we can plug into our equilibrium expression. For Kb, that's always the conjugate acid, which is acetic acid here, times hydroxide in our numerator, and then just our base in the denominator. Since water is a liquid, that gets left out. So our Kb value was given in the problem as 5.56 times 10 to the negative 10th. And we can plug in everything from our ice table. Our acetic acid concentration was X, our hydroxide concentration was X, and our acetate concentration was 0.5 minus X. And just like last time, we can ignore the subtracted X since K is small, X is also small. So we can say that this is approximately equal, sorry, changed my pen size unintentionally, approximately equal to X squared over 0.5. So when we solve this for X, which is equal to our hydroxide concentration, we get 1.67 times 10 to the minus 5th molar. And that is what we were looking to get from this ice table, which allows us to calculate the pOH as the negative log of the hydroxide concentration. So when we take the negative log of 1.67 times 10 to the minus 5th, that gets us a pOH of, that's a really ugly 4, of 4.778. And then our one extra step is to convert that to pH using our relationship that pH plus pOH is equal to pKw. We are still at 25 degrees Celsius, so pKw is 14. So the pH plus the pOH was found to be 4.778, must be equal to 14. So our pH is 9.222. And once again, we can do our little mental check. This was a weak base in solution, so our pH should come out to be basic. 9.2 is greater than 7, so this is a basic pH. And it's really good to just do that quick mental check, because one of the most common mistakes I see on base problems is stopping at the pOH and labeling it pH. Your brain's like, I took the negative log of a thing, that must be the pH. But if you're taking the negative log of a hydroxide ion concentration, that's a pOH. So if you were to stop here and do that little check, that should set off some bells and whistles. That like, this is a base, but I found a pH of 4.8. That shouldn't happen, and that can't happen. So hopefully that would help you to kind of figure out where you went wrong. But that is the general gist of it. Otherwise, bases are the same as acids. We just need that one extra step at the end to convert from pOH to pH.